Okay, one more thing I want to point over here. For example, it's 285, right? Phosphorus. So
Yes.
the more appropriate graphical representation of these ionization energies would be like this. For example, if I write its electronic configuration, it is going to be 1s2, then 2s2, then 2p6. I have filled 10 electrons. It's 15. So 5 electrons are left. Then 3s2 and 3p3, right?
Yes, sir.
Okay. So the first electron will be removed from which subshell?
3p3.
3p3. Good. So as the electron, this is, let's suppose this is the energy which is needed to remove that electron. So as that electron is removed, now it becomes p positive, right?
Yes.
So the next electron is also going to remove from 3p, but now it has a positive charge and initially it's a neutral, just p. So it needs a little more energy to remove that electron, isn't it? Because of the +1 charge it has now.
Yes.
Did you understand this point?
Yes.
Okay. Then when this electron is removed, now it is p positive 2, right?
Yes.
So to remove the third electron from 3p, a little more energy is needed. Is this understandable?
Ye- Yes, sir.
Okay, now what happens when we remove the electron from 3s?
There is an arbitrary chain.
Yeah, there is an orbital change plus the nuclear charge increase as well, isn't it?
Yes.
So it would be shown like this.
The energy increases.
Yeah, because 3s is closer to the nucleus.
Yes.
So due to as the size decreases, its energy increases, plus that nuclear charge is
Yes.
also increases. So that's why we are not observing the gradual change, a gradual increase that we are observing over here. This changes are little more greater because of the two factors.
Mhm.
Did you get this point?
Yes, sir.
Now after third shell, the next electron is removed from 2p. So actually here the subshell is changed from 3p to 3s. Now the shell is changed. So we are going to get a big difference like this. Then there is a gradual increase in the next 6 electrons.
Because of the arbitrary chain.
Subshell change, not orbital change. So a little increase and then a shell change.
Okay.
So this is the shell change, this is subshell change, this is a shell change, and this is subshell change. Is this clear?
Yes, sir.
Okay. Now you can practice along. Okay. Now after this, we have to start the mass spectrometry. So basically it is an analytical technique and it is used to measure the accurate mass of each isotope present in an element. That is one application of this mass spectrometry. And the second one is mass of organic compounds, and further we are going to reduce the structure of the organic compound. So this part is we are going to do after when we complete the organic chemistry, and this part we are going to discuss right now because we have done with the atomic structure and the atoms. Okay.
Yes, sir.
Okay. Now have a look over here. If we talk about chlorine have two isotopes that you have studied from your O levels. That one is chlorine 35 and the another one is chlorine 37, right?
Yes, sir.
So the thing is that how we are able to figure out that it has a two isotopes. For that we have performed actually mass spectrometry. This is the ray diagram. If you see this ray diagram, uh, on the extreme left, you will observe a heated filament, right?
Yes.
And that heated filament actually produces high energy electrons. One minute, please. Okay, so if you see this region, this is an inlet, and from this inlet, what we do, we introduce a vaporized sample. It means that, for example, right now we are going to analyze the atoms of an element. So we introduce the vaporized sample of any element. So if we are introducing a vaporized sample of an element, so it means we have a gaseous atoms over here in this region, which we call it ionization chamber. Is this understandable?
Yes, sir.
Okay. So what this heated filament do, it will produce a high energy electrons at this is shown. So see, this is the high energy electron. On the extreme left, I have made the diagram. So these electrons are actually get bombarded on the some atoms of the sample. For example, right now we have, introduced the sample of chlorine. So when these high energy electrons strikes the chlorine atom, they will able to remove the valence electron from the chlorine. So as a result, this high energy electron and the valence electron from the chlorine is released, and all the atoms turn into positive +1 charge ion. Is this understandable?
Yes.
As you see, these electrons are bombarded from here, so they pushes those all atoms in this region. So the sample of the atoms, the sample of the element actually push towards this region and reaches to this region. And when this reaches to this region, now they are not atoms anymore. Instead, they becomes positively charged ion. Is this clear?
Yes.
Okay. Now, if you see in this region, there are electrodes. What are the charge of these electrodes?
Positive.
Positive. And what is the charge of the ions which are formed from atoms?
They're also positive.
So what type of interaction is going to observe between these?
A repulsion will happen.
Repulsion will happen, and due to this repulsion, all the atoms move towards the flight tube. This is the flight tube. Is this clear?
Yes, sir.
Okay, and electrons are negatively charged, so those electrons are actually uh, attracted towards these plates, and as a result, now there is only the positively charged ions over here in this flight tube. Is this clear?
Yes, sir.
Okay, now due to the influence of magnetic field, and they obviously have a different mass to charge ratio, because if they have a different masses, so their mass to charge ratio would be different from each other.
Yes, but it's of the same element.
Yeah, but if the same, because if you know the concept of the isotope, that isotope has a different number of neutrons, right?
Yes.
So due to the change in number of neutrons, the mass of atoms get different. Is this clear? For example, if we talk about chlorine, there are two types of chlorine atom. One chlorine atom has a nucleon number of 35, which means they have a proton and neutrons. The sum of protons and neutrons is 35. And there is another chlorine atom whose sum of proton and neutrons is 37, isn't it?
Yes, sir.
So their mass are different. Some isotopes has a mass of 35, and some isotopes, some atoms has a mass of 37. So what happens to their mass to charge ratio? 35 over +1 and 37 over +1, isn't it?
Yes, sir.
So due to this, they are going to get separated from each other. So we got one bunch and the other bunch separated from each other due to their mass to charge ratio. Is this understandable?
Yes, sir.
Okay, and then they travel this in this tube. Obviously, the one having a mass to charge, lower mass to charge ratio have a higher speed, so they move faster, and the one with the heavier or greater mass to charge ratio would move slower, so they got behind. And due to this, they get separated. and they, after this, they are going to strike to this ion detector. This ion detector actually detects the mass to charge ratio, and after detecting the mass to charge ratio, this mass to charge ratio is going to be recorded over here, and there are two things are recorded. On the mass to charge ratio is recorded, and their abundance is also recorded, that how many number of ions strike the ion chamber have that specific mass to charge ratio. Is this clear?
Yes, sir.
And then on the computer screen, we got the result, that what we called mass spectrum for chlorine. As we have discussed that one chlorine isotope has a mass to charge ratio of 35 and the other isotope has a mass to charge ratio of 37. Is this clear?
Yes, sir.
Okay, now another thing, that the charge is only +1. So whatever the mass to charge ratio is, that is equal to the mass of that specific isotope. Is this clear?
Yes, sir.
Okay. So for a chlorine, we are going to get this spectrum. Now, see, we are getting one signal on 35 and one signal on 37. That is mass to charge ratio, right?
Yes, sir.
It means what I'm going to identify, that chlorine has a two isotopes, and as one isotope's mass to charge ratio is 35, so its mass is also is also 35. And the other chlorine isotope has a mass to charge ratio of 37, so its mass is also 37. Is this clear?
Yes, sir.
Okay. And on the y-axis, we are getting the percentage abundance. So whatever the sample we have, in that sample, there is 75% of chlorine 35 isotope, and the other isotope, that is chlorine 37, is 25% only. So that is how we are able to initially interpret the mass spectrum. So it's very easy. The number of, if we have analyzed a sample of an element only, then the number of peaks are equal to the number of isotopes of that element, if that's a pure sample. So for example, if we analyze another element and we are getting, let's suppose, 5 peaks, so it means that that element has a 5 isotopes. And if we analyze another element and we get only 1 peak, so it means it has only 1 isotope. Is this clear?
Yes, sir. But if we have multiple peaks, we can't tell if an element is pure or not.
No. Basically, the purity is identified by some other way. But if
Okay.
someone provides you a sample and it says that it's a pure sample of a specific element, and we analyze it and we are getting the multiple peaks, let's suppose you get 7 peaks, so it means that element has a 7 isotopes.
Okay.
Is this clear?
Yes, sir.
And obviously, if you don't know that that it is pure, then obviously we are not able to identify it. We got the multiple peaks, but if it's not pure and we know that it's not pure, so we are not able to figure out how many peaks are of which specific element. Okay.
Yes.
Okay. Now, this is how we calculate the relative atomic mass, AR, of an element. I hope you remember this formula.
Yes, sir.
Okay. Till here, if you have any confusion.
No.
Okay. Now, see, there is another way. Sometimes instead of the whole percentage like this, examiner gives you the scale like this. That they give you the not percentage abundances, instead they give you the relative abundances like this. Okay. So in this case, how you will calculate the relative atomic mass?
The mass is multiplied by the relative abundance, and the sum of it would be the
Very good.
relative
Yeah.
instead of 100.
Yes. And sometimes what examiner do? Examiner provide you this and they ask you to show the ratio or the relative abundance from the percentage abundances. So we will calculate it by this way. Or from this, they ask you to calculate the percentage abundance. So we will do this like it's 3 and it's 1. So we assume it's 3x and we assume x. Then we know obviously if the whole chlorine has this only, so 3x plus x is going to equal to 100, right?
Yes.
So then we calculate the value of x. So we'll able to find its percentage and then we times it by 3. So we'll get the percentage of the other isotope. Is this clear?
It's simple maths. Yes,
Yeah,
sir.
it's the simple maths. Okay. Now, can you calculate the relative isotopic mass, oh sorry, relative atomic mass of this iron atom?
Yes, sir.
Just WhatsApp me the working, okay?
Yes, sir. Sir, I've sent you the working.
Okay. Okay. Now, tell me, you tell me you have mentioned the answer is 0.607, right?
Yes.
And it's the relative atomic mass of iron, isn't it?
Yes.
So you have a 3 isotopes of iron. One has a mass of 54, one has 56, and one has 57, right?
Yes.
So do you think the relative atomic mass is going to be 0.607?
No, I feel like there is a calculation error.
Yeah, there is only a calculation error. You uh, did a mistake in putting the values in the calculator. Do it again.
Yes, sir.
It is going to be 55.7. And see, it's not the relative abundances. So you can, if you see, you can apparently identify that it is equals to almost 100, isn't it?
Yes, sir.
So you just put 100 or you do the sum as you did, both are fine. But you just uh, check your values in the calculator if you did any mistake over there.
Yes, sir. $55.9.
Okay, from that, if you are getting 55.9, that's fine. Just take the sum of these, isn't it? Is it less than 100?
It's 99.69.
So that's why you are getting 55.9. So in such cases where it's apparently seems like it is going to be 100, then just keep the 100. Otherwise, if
Okay.
it's the relative abundance is like 3, 2, or 1, then you just keep their sum as you did, as you
Okay.
told me earlier. Okay.
Yes, sir.
Okay. Okay. Now, okay, tell me, you know this kind of a working or not?
Yes, I know.
Okay. So in this, they have given you the relative atomic mass, and they have given you the relative isotopic masses of both the isotopes of bromine. And they ask you to find the abundances, right?
Yes, sir.
Okay. So, what we are going to do, for example, bromine 79 has a, let's suppose we have assumed the percentage X, and we know that the sample has the total percentage 100, isn't it? So we
Yes,
subtract
sir.
minus X to make the percentage of the other isotope, and then we substitute these values over here. And from that, we are able to calculate the value of X. So the value of X is the percentage of this isotope. And when I subtract it from 100, then I will get the percentage of the other isotope. Is this clear?
Yes, sir.
Okay. One minute, please. Now, uh, now if you look at this question, read it carefully and tell me the answers of part 1 and part 2.
The first particle is fluorine with the mass of 35, and the second particle is HCl, fluorine with the mass of 37.
Why HCl is 37?
Because Chlorine with 37 mass over charge will be 1 plus isotope of only hydrogen is 1 1. So
Okay.
mass will be 1 over 1.
If you,
And then they add.
very good. If you read the above statement, they have told you there is a compound HCl, right? That is analyzed.
Yes.
And
Yes.
they have mentioned further that some hydrogen chloride molecules was split into atoms, right?
Yes.
So it means that some of the HCl molecules stays as HCl and some splits into atoms. So it means in the sample we have HCl molecule and hydrogen atoms and chlorine atoms, isn't it?
Yes, sir.
So we have a 3 different species. Then they have told you that chlorine has the 2 isotopes and hydrogen, only 1 isotope is involved, that is hydrogen 1. Is this
Yes.
understandable?
Yes, sir.
Okay. Now you said that 35 is the mass, 35 is which substance is a chlorine, right?
Yes.
Okay. Obviously, it is going to be chlorine because hydrogen has a mass of only 1. And that is the
Yes.
smallest mass we are getting. So it means that when the HCl molecule is broken down into hydrogen and a chlorine, so the chlorine atom formed over here is analyzed as a mass of 35. That's fine. So after 35, what is where we are getting the next signal on the screen?
It's 36.
So which species would be 36?
HCl with chlorine with mass of 35.
Very good. Then which will be 37? Which species will be 37?
37 would be only chlorine with the mass of 37.
Yeah, very good. Because we got to know that hydrogen has 1 and chlorine is 35. So obviously, it's obvious that at 36, it would be HCl, but at 37, it would not be HCl, right?
It would just be chlorine. Yes.
It would be only a chlorine with the other isotope. And it is further justified as we are getting another signal at 38, which must
Which
be
is HCl with chlorine 37.
very good. So it means that at 35, it is chlorine 35, and at 37, it is HCl with chlorine 37. Is this clear?
Yes.
Okay. Now, see, in the next part, they have asked you to show the proportion of the 2 isotopes, isn't it?
Yes.
Okay. So we can work by 2 ways. Either we compare both of these HCls, one is 90 and one is 30, right?
Yes.
Or either we take both the chlorines. So one chlorine is 30 and the other chlorine is 10.
Ratio of both will be 3 to 1.
Yeah, both will be 3 to 1, so you can opt for any method. Is this clear?
Yes, sir.
Okay. Now, what they are saying in the next, use your answer C to explain why chlorine has a relative atomic mass of 35.5. So they ask you to show by this. So that's why we use 3 and 5 and then 4 in the numerator, denominator. Then we will get the same AR value. Is this clear?
Yes, sir.
Okay. Now, can you do this one and send me your work, just answers on WhatsApp?
Yes, sir. So I have sent you.
Yeah, I received your answer. Okay. Nucleon number of isotope of E is 228. Nucleon proton numbers only considered. It's radium. That's fine. Okay, how you will do this one? It's a little more trickier. Yes, Elishba, are you able to solve this one?
Sir, I'm just on the last step.
Okay.
The answer is 33.47%.
See, now the thing is that this over here, the trick is this. Let's see. They have given you, if you read this statement, so basically they have given you that the percentage of 29 plus percentage of 30 is 7.8, right?
Yes.
So it means I can, if I consider its percentage x, then its percentage must be 7.8 minus x, as we do one is x and the other one is 100 minus x.
Yes.
Did you get this or not?
Yes, sir.
So then we have to put the x with over here, or 7.8x 8 minus x over here, or the other way you can, if you are considering this one x, then you have to make it this one 7.8 minus x.
Okay.
So what you did?
I combined took the combined sample percentage and multiplied with the sum of the silicon atomic mass.
Oh, okay, okay. So now you understood?
Yes, sir.
Okay, that's fine. Okay. Now you have this whole file, right?
Yes, sir.
Okay. Then we have these. Okay, I will share it with you right now. We are done with the atomic mass calculation. Now we are going to move towards the moles, okay?
Yes, sir.
How,
First
how
chapter is done.
yeah, the first chapter is done. How good are you with moles?
I'm occasional
Okay. Do you find difficulty in moles?
in some questions, yes.
Okay. So, but first you have few definitions over here. You need to remember these definitions because these have been asked in exam. I have shared the file with you.
Yes, received.
Okay. So this is the common difference or common thing. Both are considered as MR if you see. This is glucose and this is
Yes,
calcium sulfate. It is MR, it is MR. But when I pronounce it, the full form, I will call it relative molecular mass, and here I will call it relative formula mass because it's an ionic compound. For ionic compound, we don't have a molecule. Instead, we have a formula units in the ion, in the lattice, right?
yes,
Remember, the molecules exist in covalent substances. And in ionic
yes,
substances, there is no molecule. So that's why we call it formula mass, relative formula mass. Although its symbol is same as relative molecular mass, but when the examiner used the relative term for relative formula mass, so you must understood that they are talking about the ionic compound. And if they are talking about the relative molecular mass, so it means they are talking about the molecular compound or molecules which have a covalent bonds in them. Is this clear?
yes, sir.
Okay. Now you know about empirical formula and molecular formula. The difference between
Yes,
empirical and molecular formula. The empirical formula is the simplest whole number ratio of the elements present in one molecule or formula unit of the compound, right? Like, see,
yes.
if I talk about this, can I simplify this ratio further?
No, it is in the simplest form.
So it means it's the simplest form. It's a molecular formula. But can I simplify it further?
Yes,
So it means it's a molecular formula. And when I able to simplify it, then it's the empirical formula.
yes,
Is this clear?
yes, sir.
Okay. So remember, ionic compounds always have an empirical formula. Okay. Ionic compounds do not have a molecular formula. It's so simple as ionic compounds do not have a molecule. So how could they have a molecular formula, right?
Yes,
So they always are written in their simplest ratio. And that's what its formula unit or empirical formula. Okay. Simple organic compounds. There are so many inorganic compounds who have a simple molecular and empirical formula are same. Can you give me any example? which have a molecular and empirical formula same. We are talking about inorganic compounds. We are not talking about ionic ones because ionic ones doesn't have a molecule, right?
Yes.
Can you think of any compound which have a same empirical and molecular formula?
Mm. HCl and NaCl both would be ionic compound, right?
No, NaCl is a ionic compound, HCl is a covalent.
So HCl would be the empirical molecule formula. It
Yes,
has the same empirical molecule formula.
very good. Think of any other compound. A very common compound. Water, isn't it?
Yes.
Carbon dioxide, we exhale CO2.
Yes.
Ammonia, NH3, right? So there are many
Yes.
simple inorganic compounds who have a molecule, empirical and molecular formula same, okay?
Yes.
Okay. Okay. Organic compounds have most of the time empirical and molecular formula different. For example, if I talk about methane, methane have a same empirical and molecular formula, right? But if I
Yes.
have a ethane, C2H6, it has a different empirical and molecular formula. If I have a butane, C4H10, it has a different empirical and molecular formula, right?
Yes.
Okay. Now, here I've got some examples. See, these are ionic ones. So they don't have any molecular formula, their formula unit or empirical formula. Then there are inorganic compounds with the empirical and molecular formula either same or different. Then we have organic compounds with the empirical and molecular formulas. Okay. And there is another possibility that sometimes more than one organic compounds have a same empirical formula. Like if you see C2H4 and C4H8, both are the different compounds, but they got same empirical formula. In the same way, ethanoic acid and glucose both have a same empirical formula as well. Is this clear?
Yes.
Okay. So from this, we can conclude that when we talk about the covalent ones, so empirical formula is, very insignificant. There is no significance of empirical formula, right?
Yes.
Because it doesn't help us to identify the compound.
Yes.
On the other hand, inorganic when there is a ionic ones, so their empirical formula is their identity only, their simplest ratio, right?
Yes, sir.
Okay. Now we have few more terms. Anhydrous. Sometimes you have seen that anhydrous is written before the compounds, right?
Yes.
So it is used when there is no water of crystallization present in compound. Like if I'm writing just CuSO4, then it is anhydrous. But if I'm writing some this, then they are then the prefix written would be hydrated for such compounds where there is a water present in their crystals. So you must know the difference between anhydrous and hydrated. Is this clear?
Yes, sir.
Okay. And these are the tests to identify the water or the presence of water. That copper sulfate turns from white to blue if there is a water, and cobalt chloride turns from blue to pink if there is a water present. Okay.
Yes, sir.
Okay, so water of crystallization. When we crystallize it, if you recall from the O levels, when you prepare the salt, normally we heat the solution till crystallization, and we didn't heat it till the evaporation. When the crystals start forming, we allow it to cool, and on cooling we filter out the crystals, right?
Yes, sir.
So when we do this way, then the water molecules actually gets trapped in the crystals of the ionic lattice and we get the hydrated salts. Is this clear?
Yes, sir.
Okay, so here we are done with the definitions and this. So just do go through this before the next class, which will we have tomorrow, inshallah. Okay, okay. I want one more thing for you to do. Okay, I'm sharing this file with you. Do you remember the how to calculate the empirical and molecular formula from O levels?
Yes.
Okay, so there is a one other way to find the molecular formula, which is this way, which I'm going to explain you tomorrow. But these questions are based on the previous method, which you have already done in your O levels. Okay,
Yes, sir.
so do go through those and try to attempt these questions before the tomorrow's class.
Okay.
Okay,
Yes.
okay, let me share. Just go through the method I have discussed over there and then try to attempt these questions. Then the rest of the questions. Okay, then we are going to do moles and stoichiometry, inshallah, in our next class after practicing those questions. Okay.
Yes, sir.
Okay. So is this fine for today?
Yes, sir.
Okay. So inshallah tomorrow at same time. I will try my best to start at 10. Inshallah.
Yes.
Okay.
Inshallah.
Okay. Okay. See you tomorrow. Take care. Allah Hafiz.
Yeah.